Welcome to my session and let's get started. My name is Tanel, and I'm a long-term computer performance geek. I like to build simple tools to solve for solving complex problems. And often it is possible, if you can combine a few simple tools in a creative manner, you can actually solve complex problems with them as well. So concepts, motivation, right? Just like I said, we don't want to guess or try to sort of work some magic on some sort of system-wide metrics and try to do metric voodoo and somehow figure out what the hiccups, where the hiccups come from and so on, right? We want to measure things. Let's look into the thread level. Often for many databases, a database connection is also a thread or a process, assigned to that, right? So we can actually apply the same logic to database processes as well, just like any other process, like a web server and so on, right? So I'll focus on that, and I'm not going to talk about distributed system, measurement and stuff like that. Okay, left side is the traditional old school way of measuring things. It's worth monitoring these things as well. Utilization and then throughput of your disks, whatever. That it's good to know, right? But if you go straight to the point of response time, why did it take a long time this time when I clicked the button? Why did it take 20 seconds instead of 2 seconds, right? Then we have to go straight to the point. We have to identify the threads running your stuff in the critical path of your request, and then we'll see what they were doing. And we don't only look into CPU threads, it's CPU states, we also look into when threads got stuck and were sleeping, right? So there are a few options which are practical or not, but I will cover these two. Okay, so it is possible to sample the Proc file system in Linux, right? By the way, Proc file system sampling or examination is not new. It was already described back in 1984. How you can look into Proc file system and see every process in your system is a file. In this case, in Linux, every process is looks like a pseudo directory in the Proc file system, and you can just read the contents of those pseudo files, where the kernel exposes metrics and state information to you, right? So, and I'm doing this with my OX tools suite, which is an open source tool set. It's GPL, but I think I'm gonna make it Apache or something, more permissive, because I just want this thing to spread, right? And I'll show you the two old tools quickly, just the output, and then we go to the actual eBPF version of the same thing, right? Okay, the old school PSN tool basically samples Proc file system, samples what threads in your Linux were doing, and then it shows you a summary, right? And in this case, it took a few hundred samples, and it knows how many samples it took, and it knows during how many samples some threads were in some specific state, right? And as a result, for example, in the last 5 seconds when we ran this tool, 9 threads were executed by FIO, and they were in the disk state, disk wait, uninterruptible wait state, right? So that's usually disk IO, not always, right? And six more threads were also by FIO, but they happen to be on CPU. So that on average, I guess we'll get to 16 threads in total. So for example, you could drill down saying, okay, show me also the system call, what was made. So there was this sync program, single-threaded sync program. 100% of time it was stuck, in this sleep because of this system call. It had made this system call, and now it was stuck waiting for this thing. Here I have zoomed into a specific single-threaded program only. DD is running, something, and you see 79% of time. So we sampled 100 times, and 79 times out of 100, DD was in disk wait because it had made a write system call and it was waiting to write into standard output that had been, redirected to this test file, right? Okay, so PSN only is meant for interactive work. So, things that are going on right now, you can measure them. And X-capture is then basically it's something that allows you to run similar sampling, once per second or whatever you want, and keep it running 24/7, right? If you run X-capture, by default, it's like a human readable output. It just every second it starts sampling what's going on in all the threads of this system. And by default, I only print out those which are in the D or running on CPU mode, right? Because there will be probably hundreds or thousands of threads who are in sleeping mode. So, but by default, I only print out these two states, because these two states are the ones which contribute to the system load in Linux. Okay, so can we get the same and more with eBPF? Yes. And the key to remember is that we are not going to be tracing every single event to some long, file, terabytes in size. So how do we do that? We essentially are trying to achieve this, right? Sampling all the threads in the system. Okay, so how it looks like in code? Well, if we use BPF trace, like my demo does, we can say that, hey, if anybody enters any system call, then mark it down, note it down, that, hey, there is a thread number 5000 who currently is in system call number 47, right? And we can later on map the system call number to the actual name, right, in post-processing, right? So this is for every thread in the system, when they issue a system call, they will have their own entry, that this is the latest system call where they are in, right? So, and visually it's like this, right? So it's there's a thread, it's on CPU, now it's on waiting for IO. There is it updates it updates its own slot in this state array or system call array or whatever, and it only keeps the latest state there. There is no history; it just updates the latest state. Right now, it's back on CPU and so on. And at the same time, there's another thread, right? Thread 11, right? They are going to update their own slot, right? So for every thread, we have a separate slot. Who keeps their state in there, right? And there you may also see that, hey, maybe there is some thread who does a lot of system calls, a lot of very frequent activities, and then the very frequent events, maybe 100,000 system calls per second or whatnot, right? This is not the problem for us, because all we do is we are updating this slot here, which is probably in the CPU cache, right? We are updating this, as many times as we need it, for every system call, right? So we are not tracing 100,000 system calls out to disk per second. We are just updating this slot that many times, right? So we are not afraid of having a lot of events, because we are not really logging, but we are sort of like just keeping this little shadow array of what's going on up to date. So this is the first half of the the invention, right? So the second half is now this, that we will have a separate independent program, or it can be many independent programs, who now consume this. So this left side is like producers. They will produce, or they will keep this array up to date, but they don't emit any traces, or they don't emit any data to applications or the user space. And now on the right side, you see here it's, you can write the program in different ways, but one simple way is just to make you can write an eBPF program which every second samples this array and prints out the contents of this array. So you see, first second we will just emit this. So because when the first sample happened, these threads happen to be in this state. The threads themselves keep the state up to date, right? but when we sampled it, we happen to be in this state. And now next second we sample it again, next, you know, we emit more trace or more samples, really. You know, they're not really full traces or logs or anything like that. Okay, so, and now it's time for a demo. And I already have opened this up, the file. Here you see the system call trace point. So whenever anybody makes a system call, I'm updating these little arrays which tell us information. This thread belongs to this OS, the process, you know, the thread group leader and whatever it's called, right? So you know, user ID, you know, of this process and group ID, the thread name, you know, the commenter, and now task state. That in which task are we, right? Task state are we? Are we runnable? Are we you know, in the disk or some sort of sleep state and so on? Which kind of system call are we in, right? Because we are in the system call, you know, probe here. So the arguments to the system call probe are the, you know, we're gonna get the system call ID. So that's the system call number, which you can post-process it and translate to an actual name, right? System call arguments. We can actually save all system call arguments as a tuple, right? And importantly, you see, you know, we can actually save the user space stack and the kernel stack, right? So, and of course, when the system call exits, then one option is just to say, set the system call to -1 or something, or the other option is just to delete this object so it's not going to be printed out. Okay, so now so basically it is possible to keep track of in which system call our threads were, right? And you know, you sample it once per second or 100 times per second, whatever you need, right? So it is not gonna make this part any slower. You know, if you sample this array 100 times per second, then it just, you know, you're just going to be burning, your process is going to be burning some CPU here, but it's not going to make this stuff any slower because, you know, populating the array and then later reading the array, these are like separate independent tasks. And the touch point is that state array. Okay. Okay, what else can we do, right? So now we can measure that, okay, we are in system calls. We can also now add this profile. Let's say that once per second, we sample every thread who happens to be on CPU, right? I may have 10,000 threads in the server, but if I only have 64 CPUs, then every time I sample this, I get up to 64, maximum 64 entries, right? And when I run this tool again, yeah, let's search for example, for example, we've seen some threads in the kernel mode, and I guess I have a little glitch here, but you see, you know, some of the threads were in the kernel mode running on CPU, you know, because otherwise this trace would not catch them. So they were actually doing this stuff on CPU in the kernel mode, dealing with network stuff, right? So and if I search for a profile use stack, somebody was doing malloc, you see, and if I go higher up, you see we have caught a MySQL program, a MySQL thread. This thread was doing this, right? So now you can summarize and aggregate this together if you want to understand, you know, why did you have a CPU spike last night? But let's go further now, right? I'll show you a few context enrichment examples, and let's start from the kernel, right? For example, I don't want to only show you who is sleeping, who is on CPU. I also want to show you what's traditionally been pretty hard to measure on Linux. That show me the tasks that are runnable, tasks that want to run on CPU, but they are waiting in the run queue, right? So let's see. So how do we do that? So we can actually trace when processes wake up, when threads and tasks wake up. We can trace it, or sort of populate this array saying, hey, this guy tries to wake up, right? This guy, somebody has instructed to wake up this process. This process has been put into CPU run queue, right? And this guy has not yet been actually switched, activated on a CPU, right? It is waiting. It's still waiting in the CPU run queue. Anyway, so I can just run this stress test. Let's use. I have a 104 CPUs visible in. I'm gonna say let's run 200 processes now. My CPU should be 100% busy, and then plenty of processes are waiting in the run queue as well. So and when I run this command again, eBPF trace script. So now I should see this extra fields. Now when I search for scheduler something, you see. So this, maybe I should name it better, but I should say, maybe I should name it in CPU run queue, right? And this means that this thread was in the CPU run queue, right? And now the last thing really, well, we don't have to only use Linux kernel things here. So we can enrich the context by reading stuff from other apps as well. And I'm just using an Oracle example here, right? So BPF is programmable, right? And if you know the memory structures, like it's very easy for open source tools to know the memory structures and addresses, but even for things like Oracle and so on, some of the key things like wait events and so on are easy to, pretty easy to read and look up, right? So what I did here is I said, okay, whenever any process runs this binary, instrument these two functions in that binary. So this is a BW means begin wait event, and EW means end wait event, right? And I use some magic here. So interestingly, this lookup symbol lookup didn't work in this version of Linux kernel and so on. I'll figure this out separately. But I used object dump or NM to dump out this symbol what I needed. And I know how big one element is in this Oracle wait event array is, right? And so the argument number 2, 0 and 1, the argument number 2 to this function in Oracle is the wait event number. Wait events have numbers, just like system calls have numbers in Linux, and you can translate to the system call name. It's similar with Oracle, right? Wait events have numbers, and I'm using this little magic or some simple math really to look up the offset of the correct wait event, and then I will read its text, right? So I'm not printing out Oracle wait event numbers, which are kind of meaningless, but actually the human readable text, right? And you see now I'm creating this extra map here with that hey, this thread happens to be an Oracle wait event inside an Oracle wait event. It's waiting for some Oracle thing. Oracle knows that it's waiting, right? And when it's done, I'm just going to remove it because the wait is over, right? Or maybe we'll just do some trick like that later on, right? So you see, I mean, you can run anything. You can run Oracle, SAP, MySQL, and Postgres, some random application. As long as the symbols are there in the application, and as long as you know which argument means what, you can instrument anything. That's what context enrichment means, right? And now when I just go back to, let me just search for Oracle. You see, I don't even have to run, I don't even have to run it again. You see, these are actual Oracle wait events, what you typically see for different threads, right? So in text format. And wait events also have usually often arguments or parameters. You can print them out as well. And you can play with these tools. You can watch my videos, and otherwise, get in touch if you have any more questions, or if you want to help out with building out this open source project into something usable. Okay, thank you very much, and that's all.